The examples in this video go with section 9.2, inference about the difference between two proportions. This section is on hypothesis testing. Example 1. In a clinical trial to compare the effectiveness of two pain relievers, a sample of 100 patients was given drug 1 and an independent sample of 200 patients was given drug 2. Of the patients on drug 1, 76 experienced substantial relief, while the patients on drug 2, 128 experienced substantial relief. Investigators want to know whether the proportion of patients experiencing substantial relief is greater for drug 1. They will use the alpha equals 0.05 level of significance. Part A, let P1 be the population proportion of patients experiencing significant relief from drug 1, and let P2 be the population proportion of patients experiencing substantial relief from drug 2. State the appropriate null and alternate hypotheses about P1 and P2. All right, to figure this out, let's go up here to our question. What is it we're looking for? Here it is. The investigators want to know whether the proportion of patients experiencing substantial relief is greater, that's an important word, for drug 1. So essentially we're looking for if the people taking drug 1 have more relief than the people taking drug 2. All right, our null hypothesis is going to be that the proportion of people taking drug 1 is the same as the proportion of people taking drug 2. And then our alternate hypothesis, we're going to get our clue based on what was up here in our statement of what we were looking for. We want to know if the proportion of people taking drug 1, they're the ones feeling substantial relief, is more than the proportion of people who are taking drug 2. So this is going to be a right-tailed test, and I know it's right-tailed because of the greater than sign here. All right, part B, we want to compute those sample proportions, P1 hat and P2 hat. Well, P1 hat is going to be the number of people who got significant or felt significantly better using drug 1 divided by all of the people who used drug 1. So let's see. We're dividing by 100. And let's see, of the patients on drug 1, 76 of them experienced substantial relief. Okay, so for P1 hat, we're going to have 76, those who experienced substantial relief, divided by 100. And that's going to give me 0.76. Now, P2 hat, we're going to do the same thing, but this is going to be with our second sample of those who were taking drug 2. So the total number of people taking drug 2, 200, and the ones on drug 2 experiencing substantial relief right here, 128 of them. So P2 hat, 128 divided by 200, and that will give me 0.64. So just by comparing these two proportions, it looks like the people on drug 1 did actually have more substantial relief than the people on drug 2, but we can't go by this because this is just two samples. So we actually need to run the hypothesis test here. All right, and we want to know if the fact that this is more than this, is it a freak accident? Is it unusual? Okay, and our threshold for unusual in this case is going to be 0.05. So let's see what we have. Part C, the value of our test statistic. Okay, to find the test statistic, here's our formula for it. This looks extremely complicated here, but really notice we're running a z-test. We're going to be looking at P1 hat minus P2 hat divided by, now this is just a plain old P hat, and here's my formula for it right here. This is the pooled proportion. Okay, so P hat times 1 minus P hat times 1 over N1 plus 1 over N2. All right, so let's see if we can get all that in there. All right, our test statistic is going to be P1 hat minus P2 hat divided by, all right, now our pooled proportion, the P hat, that's going to be x1 plus x2 divided by n1 plus n2. In other words, 76 plus 128, these are all the people in both samples who felt substantial relief, divided by 100 plus 200, those are all the people that were included in both samples. All right, and let's put this in the calculator. And this is going to give me 0.68. So the denominator here, this is going to be 0.68 times 1 minus 0.68 times 1 over 100 plus 1 over 200. And then we're supposed to square root everything down here in the denominator. All right, let's put this in the calculator and see what we get. My calculator, when I round it, is giving me 2.100. Okay. Now it's asking me to compute the p-value. All right, so we're going to need to draw a picture here. A normal population is going to follow this bell-shaped type curve. The mean is going to be right here in the very middle. Now, this is a z-score over here, which means that the mean is going to correspond to 0 as a z-score. And if this is 1 standard deviation and this is 2 standard deviations, then 2.1 is actually going to be slightly past that. And we're going to be shading to the right, remember, because this was a right-tailed test. So the area we want is actually all of this right here. Now, I'm going to use table A2 to figure out what that area is. But table A2 is going to give me all of this area back in here. And so in order to figure out what my answer is, or my shaded area, I'm going to have to do 1 minus whatever the area I get for this side is going to be. Okay, so let me check out table A2. Table A2 tells me that the probability of being in this unshaded area over here is 0.9821, which means that the p-value that I want for part D is going to be 1 minus 0.9821, and that's going to give me 0.0179. All right, part E, interpreting the p-value. All right, the probability of observing a test statistic as large or larger than 2.10 is, this will be our p-value, 0.0179. This is unusual. Because remember, our threshold for unusual was 0.05, and 0.0179 is less than 0.05. So this is, in fact, unusual. So 0.0179 is less than 0.05. And then part F, what is our conclusion? Well, since we did get an unusual situation here, we are going to reject that null hypothesis. Example 2, A sample of 200 voters over the age of 60 were asked whether they thought Social Security benefits should be increased for people over the age of 65. A total of 95 of them answered yes. A sample of 150 voters aged 18 to 25 were asked the same question, and 63 of them answered yes. A pollster wants to know whether the proportion of voters who support an increase in Social Security benefits is greater among older voters. He will use the alpha equals 0.05 level of significance. Part A. Let P1 be the population proportion of older voters expressing support, and let P2 be the population proportion of younger voters expressing support. State the appropriate null and alternate hypotheses for P1 and P2. All right, let's go back up into the problem and find out what question we're actually asking. The pollster, there it is, wants to know whether the proportion of voters who support an increase in Social Security benefits is greater, there's that important word, among older voters. In other words, we want to know if the older voters is greater than the younger voters. In our first sample, since they're over the age of 60, these are going to be our older ones. So we're actually trying to figure out whether the proportion in the first sample is more than the proportion in the second sample. And this looks like it's going to be another right-tailed test. Okay, so our null hypothesis is that there's no difference between the two proportions. P1 is actually equal to P2. And our alternate hypothesis is going to be that P1, the older voters, proportion is greater than P2, the younger voters' proportion, as far as raising those Social Security benefits. All right, let's see, Part B. Now we're going to compute the sample proportions, P1 hat and P2 hat. All right, the sample proportion for P1 hat, this is going to be all the people over the age of 60 who are in favor of the Social Security benefits divided by all of the people who were questioned about this. So let's see, we've got 200, and let's see, 95 of them said yes. So P1 hat is 95 divided by 200. And if we look at that in the calculator, this is going to give me 0.475. All right, P2 with the hat, this is going to be the number of younger voters who voted in favor divided by all of the younger voters. Right? So let's see, they looked at 150 younger voters and 63 of them were supporting. So P2 hat, 63 divided by 150. And I am going to round this out to 3 decimal places, just like the first one was round. Well, the first one ended up being 3 decimal places. It terminated. And never mind, it terminates also. I got 0.42. I'm just going to put that 0 on there so they have the same number of decimal places. Okay, the test statistic. Okay, again, we're going to be doing a z-test. And this one's asking us to do the p-value, but I'm actually going to do the critical value method just so you can see both of them, a p-value and a critical value way to do these. And unless the problems tell you specifically you have to use p-value or you have to use critical value, you can pick the one you like best and use it. Okay. All right, since we're going to do the critical value method, we're down here, we're going to find the test statistic. We're still finding a z-statistic, and we're going to use the exact same formula we used before when we were doing the p-value method. Okay, that's going to be P1 hat minus P2 hat over this pooled proportion down here. Remember, which is x1 plus x2 over n1 plus n2. All right, and so let's figure this out. Let's do the pooled proportion first. Now remember, the pooled proportion, these are going to be all the people who are in favor from both samples. So this is going to be 95 plus 63 divided by all the people who were sampled. So there were 200 in the first sample, and there were 150 in the second sample. All right, let's put this in the calculator and see what we get. And this one I will need to round. I'm going to round it to 0.451. All right, so our Z statistic, we're going to look at P1 hat minus P2 hat divided by P hat times 1 minus P hat times 1 over 200 plus 1 over 150. And then remember, we're going to square root everything down here in the denominator. All right, let's put this in the calculator and see what we get. All right, and this is going to give me 1.023. All right, part D. We want to compute the critical value. Okay, so let's go down here and see how we're going to do this. Okay. The critical region is going to come from our alpha value. Okay. All right, so we're going to need to draw a picture. Well, we will draw a picture for this. But first of all, our critical value is going to come from table A2. Now remember, our threshold level for something being unusual is 0.05. That was told to us back here. Okay, so our critical value is going to be based on that 0.05. So our picture, what we're looking for is, and again, here's my normal curve. And remember, the mean's going to be right here. Now, this was a right-tailed test. So what I'm trying to figure out is, what number is this right here so that the area to the right is 0.05, my level of being unusual, okay? This is my critical value right here. Okay, so actually I can pull this number directly out of table A3. All I need to do is go down to the bottom line, to the Z line, and I'm going to be under the column 0.05, and that's going to give me 1.645 as my critical value. Okay, so what that tells me is that this number right here is 1.645, and I know that all of the area to the right of 1.645 is 0.05. Okay, all right, so now we have our critical value. Now we want to interpret that critical value. Okay, well, if the null hypothesis is true, then the probability of seeing a critical value of 1.023 is more than 0.05. And I know this because on the number line down here, if this is 1.6, this point right here, then I want to know where 1.0 is. Well, 1.0 has to be in between 0 and 1.6. Remember, anything to the left back here is negative, and if we say that 1 occurs right here, then 1.0 is just going to be slightly to the right of that. And this, my critical value, my Z value, does not fall inside the shaded region here to the right. Okay, so this probability, whatever it is, if from here out is 0.05, this would add more to that probability there, okay? So we know that the probability of getting a test statistic of 1.023 is going to be more or greater than 0.05. All right, so for part F, we're going to state a conclusion. We will not reject the null hypothesis. And we will not reject that null hypothesis because our critical value 1.023, I'm sorry, our z statistic is actually less than our critical value of 1.645. All right, so the key here when you're doing critical value is if your test statistic falls inside the shaded region, then you accept the alternate hypothesis or reject the null hypothesis. But if your test statistic is in the unshaded region, then you will not reject the null hypothesis. Be sure you do not ever accept the null hypothesis, okay? We either have enough evidence to reject it or we don't have enough evidence to reject it.